This is my follow-up video on my last video about Neyman Pearson's lemma. And in that video, I gave a brief introduction to what is Bayesian's methodology on likelihood ratio test. I couldn't find any good video on YouTube that explains the Bayesian's methodology, so I thought I'll make one for students who need some help from the textbook explanation. So let's start with an example. Here they have two coins, coin 0 and coin 1, and this table is a recording of tossing each coins 10 times and recording how many heads they have got. And it is also believed that coin 0 has a probability of 0.5 and coin 1 has a probability of 0.1. And as always in any experiment, we have hypothesis here. The hypothesis 0 is that the coin that we tossed is coin 0. Based on any probability that we see, we believe that it's coin 0, and hypothesis 1 is the coin 1. And likelihood ratio here is just a ratio between the values that we get. We can directly take the values from the table here. If we consider 2 heads, it's probability of coin 0 when we got 2 heads by probability of coin 1 when we got 2 heads, and it comes about value 30. And this gives us a result that the coin 0 was more likely to happen than coin 1. This is the basic of likelihood ratio. Let's go into Bayesian methodology. In Bayesian methodology, if we have to have a ratio for a probability, first of all, we need to figure out the posterior probability. And if we need to figure out the posterior probability, we need to have the prior probability. So let's derive the equation for the Bayesian methodology. Let's take each coin separately. To find the posterior probability of coin 0, again we start with our conditional probability formula, where probability of h naught given x is equal to probability h naught x comma x by probability of x, and then this goes back to the formula of probability of x given h naught and probability of h naught by probability of x. And when we divide the probability of h naught given x by probability of h1 given x, this is the final formula that we get. This means that the first part of the formula means it's the prior probability, which is probability of h naught by probability of h1, prior probability of both the coins. And the second part is called as the likelihood ratio. This is what we obtain from our data. This is what we believe, and this is what we obtain from our data. And this is a table that gives the posterior probability, not the posterior, the likelihood ratio, which we get by dividing these two values. So how would we go about choosing whether it's h naught or h1? So we bring in a concept called critical value. If it is greater than 1, here, since we don't know probability of h naught and h1, we write the formula directly as probability of h naught of the prior ratio into likelihood. If it is greater than 1, then we choose h naught. Otherwise, we choose h1. But since we will not know what is a prior probability, or we have to come up with some value for the prior probability of the two coins, we can in order to obtain a formula, we can send these to the right hand side and make that as a critical value c, which depends on the prior probability. So prior probability heavily influences the critical value c here. If our likelihood ratio is greater than a critical value c, it means that the h naught is true, otherwise h1 is true. In any test, we need to figure out what is the error that we'll obtain. Basically, it's type 1 error and type 2 error. To obtain type 1 error in this case, again we have to look at the probability of h naught getting rejected when it is true. And based on our table, we can clearly see that if we take the value 1, if we take our critical value as 1, considering both the probability of both the coins are same, the prior probability of both the coins are same, then above 6, h naught would fail. We would have to reject the h naught. And this will be our type 1 error, 0.18. And this we calculate from the first table where we sum all the values from 7, 8, 9, 10 of coin 0. And the second error that we have to figure out is the type 2 error, which is accept the h0 when h1 is true. This is probability of x less than or equal to 6 when h1 is true, and that comes around to 0.35. So both of these values are when we choose our critical value as 1. Let's say we choose our critical value was 0.1. That means that probability of h0 by probability of h1 is 10. We already believe that the number of hits that we got is from the coin 0. That we have a high confidence that it's coin 0 prior to the experiment itself. Then in that case, again, when we calculate the probability of the rejection of h0 given h0 is 0.01 and acceptance of h0 given h1 is 0.85. And this is the basic of Bayesian methodology for likelihood ratio.